Thank you for coming to this talk. It's the last day. I feel very loud. It's the last day. It's after lunch. I thank you very much for choosing this talk to come see. I promise you it won't be so boring. I'll try. So, how many of you have heard the fact that document databases are schemaless? Raise your hand. Who thinks that's a scary thought? Yeah, you be confident, raise your hand. Yeah, that's a scary thought. If used improperly, it can be a very scary thought. Document databases have always had this kind of tabloid-esque type of information coming about them. That field flexibility for all documents is amazing. You don't have to deal with migrations and schemas. You can just get building and start going and building your application very quickly. You don't have to worry about the data model. Exactly, what data model, right? Whenever you talk about document databases, because the words schemaless and flexible document are top of mind for you, you don't really think that a data model is necessary. You don't even think that it is required when you are building with document databases. But that is very, very far from the truth. While flexibility is great in theory, it's actually not that great in reality. In fact, reality dictates that all data has some sort of structure. Otherwise, it would be meaningless, right? No matter how much data that we collect, it doesn't make any sense unless we make use of all of the structure that is surrounding it. The way we interact with it, the way that we process it, the way that we use it in our applications requires us to make use of that structure that is hidden deep within the data that we collect. And that is why I'm here today to talk to you, and not blast your ear, hopefully, about the developer's guide to data modeling with document databases. So I used to be a senior developer advocate for MongoDB. I just left, and so now I'm enjoying my life in Porto for the time being. The goals of this session is to show you that there is a process, there is a way to create a data model for document databases. We're going to go through what that is, explain each phase in detail, and then we're going to actually apply what we've just learned to an example. In this case, I'm actually based in Las Vegas, so we're going to go through a casino floor analytics application and apply the phases that we've learned step by step so that you see how it's actually being used. And then finally, we're going to understand what I think is more important, and that's what actually are we modeling for? I know we want to get to the root of it. You just want to display some diagrams and get to the model, but it's also important to understand what we are doing it for, because that also helps shape what the eventual data model will look like. It is possible to develop a data model for document databases. It's necessary to create one. Please, if there's anything that you take away from this talk, it's that just because it's schemaless does not mean you don't need a data model. In fact, the one that you create, the one that you design, the one that you use with your application greatly impacts what your application is going to be like. This is a little small. So let me see if I can zoom in here. So this is a Reddit post that shows, in this case, they were using MongoDB, but they were very detailed about what their data model looked like. And they were impressed so much so that they wrote an entire post on the MongoDB subreddit about why the performance was just incredible. At the same time, if you have the wrong data model, you're going to get something like this. You're going to get a lot of Stack Overflow questions, community forum questions that say, I'm having lots of trouble, or I'm only trying to process 1,000 documents and it's 8 seconds long. What's going on? That's probably the data model that you're using. So this is just another point to say that the type that you develop really does matter and can affect your application. So we're going to build a data model in 3 phases. I'm going to leave it here because some of the code I've checked, it's kind of hard to read, so I'm going to have to be zooming in and out a little bit. So the first phase that we're going to do is to make sense of your workload. What does that mean? We want to gather everything there is to know about your data. What does it look like? What operations are you running? We're going to have a list of inputs. And so let us zoom in here because it's very hard to read from the back. So the first thing that we want to gather is listing, qualifying, and quantifying all of the operations. What queries are you running in your application? What are the most important ones? What are the ones that are not running at all? You need to look through all of this logs and statistics, which is the next thing that we'll talk about, and see where are your actual queries running. The more information you can get, the more you can describe how you're using your data, how your application is interacting with the data that you are using, which collections you are querying the most, and which ones you may be querying across multiple collections when you could be combining them because they're supposed to be queried together. These are the types of questions you want to be answering when you're making sense of your workload. You want to get current and predicted scenarios. So if you have an application that runs and you may have some spiky traffic on certain times, you want to collect that type of data. You want to get the maximums. What does your maximum traffic look like? What do your minimum traffic look like? What does average traffic look like? These are the quantifying portions of what your workload means. You may also want to collaborate with a business domain expert. So yes, us as developers, we kind of are in the weeds sometimes and we know what we're working with, or we only see the feature or bug that we're working with. Sometimes it's always good to speak to a business domain expert so that you can account for other things that you may not be working with or be not as familiar with, or something that you just is out of your realm of what you've been working on in the last sprint or so. These are all great sources of information to help you make sense of your workload. So we take all of these inputs, and out of this initial phase, you're going to get some outputs. So the outputs that you will receive are the operations that you run, the queries that you are running, the data sizes that you're working with, the assumptions that you're working, or the indices rather, the indices that you're working with, and the assumptions that you are making as part of your application. Out of this entire process and out of this entire phase, once you've made sense of your workload, you will have these particular outputs to work with, which will then feed into this next phase. So you take all of these pieces of information, you know it, you know every query, you know the averages, you have the quantifications of how many times they're running, you have your scenarios, and now you're going to feed it into this next phase. That next phase is to now map out and identify the relationships that are part of your application. So having all of that data available helps you see those entities very quickly, and it helps you try to map out everything that is part of what is actually being run and what could run. So what does mapping out and identifying relationships look like? The first part is to quantify and identify relationships. So you all may be familiar with this type of crowfoot notation, right? We've seen this in a relational database, relational data model before when we were mapping out relationships. We have our one-to-one relationships, you have our one-to-many, and we have our many-to-many. And those are also still found in document databases. This is still a very same way that we're able to model the relationships in document databases. So you want to map those out as well because they do exist. And one other thing that we found, because of the way that we are collecting so much more data now, and with the rise of how much data we're able to capture, we also have something called 1 to zillions. So this could apply to things like IoT sensors, where you're just getting so much information per second, or even now when you're dealing with the scale of Amazon or Microsoft or Netflix, anything like that, you get petabytes of data per hour or even per second, depending on which team that you're working on. The massive amount of data pretty much led to this additional type of relationship because the existing ones that we had couldn't really fit or capture what that kind of relationship was like. And adding to that, we have the numeral notation of how we note that. So if you do have some sort of 1 to zillions type of relationship, as part of that, you'll want to list the minimum amount, which is usually 0 or 1. you'll want to list the likely amount. So this is where your averages come in. This is where your current scenarios from the data that you've received from making sense of your workload. This is possibly the number that you can calculate of likely, your average use case. And then you have your maximum. This is your, your spiky traffic, really top of the line number. This is the maximum amount of this particular entity that you'd be seeing in this relationship. Once you've quantified and identified those relationships, the next part is to decide whether to link or to embed. And I know some of you who's here thinking, what is linking and what's embedding? Who doesn't know what linking and embedding is? That's fine, that's why you're here, right? So, linking and embedding is not so difficult to understand. Linking is something that's going to be very familiar to you if you've already worked with relational databases. So we have a document here. In this case, it's a casino. And we have some information about this casino. What's the name, its ID, the year that it opened, the nicknames that it has, etc. And linking is literally getting an ID here, or a reference, and having an additional document that links to that particular information. So we have the ID here that says this is the owner, and we have the specific owner information held in a separate document there. So it's very similar to adding a foreign key to a particular entity here. And in this case, we're putting a link to it in a document. Embedding, on the other hand, is pretty self-explanatory. The word itself, embedding, explains what it's doing. So embedding means we will take the information that we need. In this case, when we are querying this data about the casino, we usually need the name, the headquarters, and when it was founded, and we're simply going to embed that into the document itself. And that is it. That's the difference between linking and embedding. So you can think of it as linking is very close to having a foreign key relationship. And then embedding is actually taking the information that you need that might be stored in a different collection and adding it to the same document. You usually want to do this if you have to query that type of information together. So that's when, again, making sense of your workload, if you find that your most important queries are running so many joins, which is can be done in a document database, but if you find you're running so many joins or going off across multiple collections to gather all of that data to bring back to your application, you might want to rethink and get the ones that you need and actually embed it into that single document, because data that is accessed together should stay together, and that's how it should be stored. And you'll see that's the information that we've embedded from the owner information. So we can just add that as another subdocument. So, how do we decide to link or embed? These are just some general guidelines. Obviously, you have to look at what your data is like, but these are generically what you would want to do. So let's first look here. If the type of relationship that you are deciding on is to embed a document in the parent document, meaning in our last example, we took some of the information from the owner collection and embedded it into the casino document. With any one-to-one relationships, you'll find that you'll have single reads and no joins when you do it in this way. Same thing with one-to-many relationships. And if you do have many-to-many relationships, it's still a single read because, again, you're putting all that information together. You're putting it in a single document to be able to access it directly in one query. You have no joins. However, there can be some duplication of information. So if you still need that owner collection and you still have all of that listed out in separate documents, but you decide to embed just the subset that you need into the casino document, there is some duplication of information. But overall, this is okay, especially if you need to access that data together, and in the long run it gives your application a better performance boost to have all that information together in one read. Now, if we linked in the parent document, meaning similar to the foreign key relationship, you will find it's quite similar, right? So one-to-one relationships, you'll have smaller reads, which could be faster, but you'll have multiple reads. You'll have many reads because now you have to access both collections or multiple collections depending on which things you are linking to. And it's the same across all of the relationships. The one thing to keep in mind is if you do have something like a 1 to zillions relationships, you most likely want to link everything. Because if you're embedding and you have zillions of relationships and you're putting all that extra information in there, you're going to have a bad time. So usually with 1 to zillions, linking is the way to go. So great, now we've taken a look at all of the data that we have. We have all of the inputs there. We've mapped out all of our entities. We've looked at the relationships that are as part of the data that we have had in the first phase. And now the last part is to apply design patterns. But there's a caveat. See, at the end of phase 2, you actually have a data model already. And this is something that you can use right away. So this third phase is actually an iterative approach, meaning if the data model that you have at the end of phase 2 is already working and your application is not seeing any type of performance issues, or you don't have new data that you have to accommodate for, then maybe you don't need to apply any design patterns, because the complexity that's added by applying these design patterns may not outweigh the simplicity that you already have, especially if your application is working as intended. So keep that in mind, that as your application starts to grow and you do start finding that you're having bottlenecks, or you do start finding that there are issues in your application, then you can get to phase 3. You can go through this methodology again, go through phase 3, and try to apply some of the design patterns that we'll learn about today. There are many design patterns. I'm not going to go through all of them. I'm already thinking that should be a separate talk, but we will go through a few. So what is a design pattern? We've heard about this before. We may have seen this in computer science in general, and it's the same thing here in a data model. It's a reusable solution to a commonly recurring problem. And in this case, it's a data structuring model that solves a common document data model use case. And I say this here because, we like to get paired in with the NoSQL tag, but NoSQL actually encompasses a whole bunch of other data models. NoSQL's document databases, graph databases, key value pairs, wide column stores. So that doesn't mean you can apply these design patterns to any NoSQL data model. These are specifically for document databases. So what design patterns are available? We'll start with the polymorphic one, because that kind of is the basis for most patterns here. So the polymorphic pattern pretty much states, and you may have heard of polymorphic before, is that the shape of the document can change. But more specifically, in the polymorphic pattern, let's say you had to keep a whole range of documents in a single collection. If those documents have more similar fields than different fields, then it's generically called the polymorphic pattern, right? You will have some fields that may pertain to only a particular document, depending on a particular field. So what does this mean? Let's say we have a list of athletes that you're going through, and in the casino, maybe you have some sports bets and you're looking through all the different athletes and their stats or something. In this particular case, we have a single collection of athletes, and the first one here we see is Kobe Bryant, the late great Kobe Bryant. And we'll see that we list the sport, the athlete name, and the career earnings, and those are the similar fields that we're keeping for all the athletes in this particular collection. If we look at our next document here, the next athlete that we're storing is Serena Williams. Now, I don't think Serena Williams plays basketball. No, I don't think it's been publicly shown anyway, but professionally, she plays tennis. So in this sense, we're going to keep also her sport, also her name, also her career earnings, but because she plays tennis, she has something different. She has an event here, because the way tennis is played, you may have singles, you may have doubles, which we'll get to in a moment. So that's just the whole point. It's a different shape. Polymorphic means that this document can exist in the same collection. And more specifically, we can even further change Serena's document here, because tennis is a different event. So here we can actually list the event as yet another array, and in this case keep track of the singles and the career tournament she's won there, as well as doubles, etc., etc. So polymorphic is the basis for most of these design patterns, because it relies on the fact that these documents can change and can exist side by side in the same collection. The next pattern I want to talk about is the attribute pattern. So here we see, well, the attribute pattern, let me tell you about it first. The attribute pattern is useful for problems that are based around really, really large numbers of documents. And within those documents, there's a subset of fields that you want to query on. So in this particular example, we have a list of a movie and their releases. Let's say we want to search on the particular release date. The problem with searching by release date, at least in the way that this has been modeled, is that there's different release dates for different countries. So if you were to search on release date, you're going to have to create very many indexes, and you're going to have to do it on each individual release date field that is part of that document. So instead of doing it this way, what you can do is apply the attribute pattern. And what we do is we take that particular field that we know we're going to be searching on, and we just apply that as a subset. We apply it into an array, into this list of movies, and then we are able to query on just the location and the date. So not only are fewer indexes needed, because now what your indexes look like are this. Instead of each individual separate country would you need to have an index on, you would just have to create these two if you have applied the attribute pattern in this way. And because of this, queries are also simpler to write because now you don't have to check every single individual release field. You can just check this particular location and date in the subset. Lastly, one that is very popular and very useful and one you can apply right away is something called the document versioning pattern. So if you're ever faced with the need to maintain previous versions of documents, but you still need to keep a record of what's most current, the document versioning pattern is something that is very, very useful. So one really good example of this is something like insurance. Insurance is the most boring thing ever, but I tried to make it a little bit more fun here. So in insurance, when you usually purchase insurance, most people go with the standard policy, right? You have your basic things that are there, and you start out with whatever you initially insured. So in this case, we have a document for Bilbo Baggins, and in the very first time that he acquired this insurance policy, he only has the elven sword that he needs to insure. So at this moment in time, this is the current policy, this is how it is right now, this is the only thing that he needs. As we continue to grow, and let's say Bilbo acquires a one ring, well, now the current policy needs to change, right? He not only needs to insure the elven sword, he wants to now add this one very precious ring to his insurance policy. So because we need that current state, this is now going to be revised. We see the document versioning here, simply a field that shows what version of that particular document is. And to keep track of that, we now have to add another document. So now we have to add a separate collection that shows all the revisions that have been made. And so when this change occurs, we now have to add what's called a new policy revision document. You can name it what you want. In this case, it's the new policy revision document. And we have a history now of what their policy looked like prior. So as more things are insured, as things are taken away, as things change for the current state of Bilbo Baggins' insurance, the current one will always stay current. And you can know that because you can check the revision. And you'll also always have the previous versions by adding a new document to the policy revision collection. So things to note about this. It's very easy to implement even on existing systems because again, what's needed here is just one field that shows what revision it is on, and you may have to open up a new collection to keep all of the history. There's no performance impact on the queries on the latest revision because you only have to query against your current collection. The cons of this now, though, is that it does double the number of writes. So every time it does change, remember, you have to add another document to the policy revision collection or wherever it is you're storing your history. So keep that in mind. And then one other thing to keep in mind is you have to make sure your queries target the correct collection. So make sure it always goes to your current one, make sure to name your collection, something along the lines of, you being able to figure out that that is the current state. Some other assumptions of the data that you need to keep in mind for this particular pattern is that usually the documents don't have too many revisions, although in this case, this should suffice. So insurance, it can change over time, but it won't have hundreds of changes or thousands of changes. So that is one assumption that is made when using this particular pattern. And there's also not too many documents to version, meaning that this is the main document you'll be working with. You won't have multiple documents that hold the same particular information. Either you store it all together, like before, data that's accessed together stayed together. You don't split it apart, especially when you apply this particular pattern. And that's just 3 of the patterns that are available. So we spoke about polymorphic, and we spoke about attribute pattern, and we spoke about document versioning. Let me zoom in here so you can see. So document versioning, you'll see the use cases that they are usually used for are things like catalogs or content management, personalization, and single view applications. If we take a look at the attribute pattern, that is also used in catalog or content management and single view patterns. And then polymorphic, which is the one that we did speak about, is used on the same ones as well as mobile. So this is just, again, a generic chart of what types of patterns you usually see in different applications because they're the best use case for those types of applications. So these are the other patterns. And you can come and ask me later if you want to know about a particular one. There's the bucket pattern, which is usually used with IoT. There's the outlier pattern, pre-allocated, computed, when you have a lot of things that you're continuously, repeatedly computing and you access all the time. You can do that through this pattern and it makes it much faster. But we don't have time for that. And that is it. After you apply all of the design patterns that are necessary for your data model, you now have a data model, but that's not the end. Again, you continue to go through this. As your application goes and iterates through the next versions, you may find you may need to go through this 2 times, 3 times. You may find that you need to apply different design patterns if you're finding that you're accessing your data in a different way. Or if your workload changes, what things used to be the most important queries may no longer be the important queries for whatever reason. So this type of methodology, going through each of these phases whenever you find that you're having performance issues or you need to introduce new data or you're changing what data is important in your application, is something that you can go through and continue to evolve. So now we know the how, right? What are we doing? Let's go through a very quick example of how to apply this methodology. So first phase is making sense of our workload. And we're going to do this with a casino floor analytics application. Who has been to Las Vegas? Okay. Who has been off the strip in Las Vegas? Okay. Oh, you had me there for a second. I was surprised. Okay. So when we go to Las Vegas and you step into a casino, it looks like this, right? I mean, this is an outdated picture, but you have your table games, you have your slots, you don't know what time it is, you're confused. That's the point. They want to keep you there so that you can give all your money away to them. So as part of this casino floor analytics application, we've been tasked with creating something that analyzes how our slot machines are doing. Basically, there's all kinds of slot machines made from different manufacturers, different bonus structures, different types of games. What's one interesting thing to note is that the location of the slot machines actually give you either better or worse chances when it comes to your odds against the house. All of these things are calculated, and we want to play a part in analyzing which slot machines are doing better, which ones are doing worse, which ones should we, transfer out for something new. So part of this application, we're going to be capturing lots of different pieces of data. We want to capture when people win jackpots, right? How much those jackpots are. We want to capture the win chances of these individual slot machines. Sometimes we have slot machines, if you've ever seen, where it's not just a single slot machine where you have to get a particular line. There's one where you can choose a game, right? Jacks are better, Texas poker. There's like 16 different games on a single slot machine. So that's something else that we have to keep in mind when we're analyzing these different types of slot machines. So first phase, list our workload operations. So as part of this, we're going to go on the side of simplicity, and we're going to say, we're going to find that the queries that we are running as part of this application are these. First, we want to see how long each player plays on a particular slot machine. We know that this is a write operation, and we know that every time a player inserts their membership card into the slot machine is something that we can record and tap into. So we know when they put it in, we know when they take it out, we know when they move to a different slot machine. We can capture those pieces of data because we write that in our application. We have the win chance rate. So this is something that is configured and plays a role from the Nevada Gaming Control Board. So these are things that we read because they do change often. We want to see anomalies in the win rates. So this is to help us capture some of the table games, but these are just other operations that we include as part of our analytics. But there are also anomalies in when people win on the slot machines. We want to see the top slot machines played. So again, it's another read, and this time we do some analysis on the play times of the slot machines, and we replay those replay conversions, meaning how many people go back to that same slot machine, how many feel this is hot, it's 5 minutes and I'm going to win that jackpot, how many people go back to a favorite. And finally, we find jackpot increases, which is going to be a write. So there's this set of slot machines in Las Vegas where, if you may have seen them before, where there's multiple slot machines and they all contribute to a single jackpot. Sometimes they actually are tied to other casinos who are of the same type of similar jackpot. And as more people play on each of these slot machines, as no one wins, the jackpot grows and grows and grows and grows. So in this case, we want to keep track of that kind of slot machine as well. And we want to see how much the jackpot increases for that. So we've made sense of our workload. We have listed the top operations that we're going to run through. And now we want to map out and identify these different types of relationships. So after looking at the queries that we are running, we find that the most important relationships are these. We find that we have one-to-one with slots and casinos because each particular slot machine has its own serial number. There can't be a single physical slot machine that is part of two different casinos. So this is a one-to-one operation, or relationship rather. We have slots and bonuses, which are one-to-many. One slot machine can have multiple different types of bonuses depending on the hour of the day, depending on the game that is selected that is going to be played, and depending on the win rates that are being set. We have casinos and slots, which are also one-to-many. We have jackpots and slots, and player and memberships. So a player can have multiple memberships. If you may not know, but a lot of the casinos on the Strip, they're really just like most of the world, a few conglomerates who own most of them, right? So Harrah's actually owns Harrah's, Caesars, Flamingo, Paris. Those all actually don't belong to Harrah's anymore. They got sold to Eldorado. And then the Wynn, Sands Corporation owns Wynn, Encore, etc. So out of this, a player can have multiple memberships per casino that they are in. And this is the listing of those most important entities. So as we start to iterate on our data model, we find that we do need to apply some design patterns to this particular one, and we'll go through them. Super tiny, we're going to zoom in. Let's go. So we find for our slots, we want to keep track of the type, we want to keep track of the manufacturer, we want to know which location it's in, we want to know the serial number, and we want to know the win chance and the bonuses. Go over them really quick so it makes a little sense. For our jackpots, we are keeping what the current total is, how much is the jackpot at that particular moment, and we want to show which participating slots, which group of slots are feeding into that particular jackpot. For our casinos, again, we have an object ID to identify them. We have the name, a type. We also have the top performing slots that are part of that casino. Sometimes it's the ones that are by the edge. Sometimes it's the one that's near the bar. You never know. And we also want to know the floor manager for that particular casino. And then we have the players, right? The most important ones. Those are the ones that give us all the funding and keep us going. So we want to know, are they a high roller because they get those extra perks? We want to know what memberships they have, their contact information, etc. And so this is what our application or our data model looks like so far. And the first thing you'll see here is we've decided to embed these particular subsets of information. So for slots, we have embedded the bonuses information because we always access that at the same time. We want to know when we are looking at this particular slot, a bonus is something we find that we're always looking into. When we look at our jackpots, we obviously want to know the participating slots that are part of this jackpot, so we choose to embed that in there. For our casinos, we have embedded the top slots, and for the players, we've embedded their membership and their contact information. Even though these may be held separately, even though these may be stored in a separate collection for other things, for this particular application, we've decided to embed them because as we access them, we need all of that information together in a single query. You'll find that we use the document versioning pattern here for slots. So we just, similarly to the insurance application, we add a revision field because as the slots change, as the win chance changes, maybe it is actually being decommissioned because it's an older slot. We want to keep track of what the state of that current slot is. And similarly to our players, sometimes your contact information changes. Sometimes you're no longer a gold star member and you don't get free rooms anymore. You're just a little peasant who doesn't have a really high membership level. So those types of changes are things that don't usually change too often, but are still necessary to keep track of. And so in that case, we use the document versioning pattern for those particular entities. And here we use the attribute pattern for the slots, because for most slots we find that we do query on the particular bonuses. We want to analyze what types of bonuses may be drawing people to those particular slots. If we find that the bonuses are more enticing or they're higher or they're of a particular number, we find maybe that has some sort of influence on which players choose which slots. And then we have polymorphic. So this is our standard slot document, but we can also have one that's like this, right? We can have one that has different game bonuses. So this one would apply maybe to a slot machine that has different multiple games that you can select and choose from. So then it would have different types of bonuses as part of that. Or it could look like this. This could be one of an older slot machine, one that has a maintenance log because it has mechanical parts. They're not all digital anymore like everything that you see currently. And in this way, we see an implementation of the polymorphic pattern because all of these different types of documents, though shaped differently, are existing in the same slots collection. And that is the data model that we have developed for our analytics application. So now that we've gone through the phases, now that we've actually applied it to a particular use case, the actually most important question we should ask ourselves is, what do we model for? Do we model for simplicity or do we model for performance? And it depends. If we're modeling for simplicity, you're usually a small or early stage app. You want to take a look at the size of your document, or your project, excuse me, and you want to take that into account when you're developing your data model. You want to see the size of your team. If it's a single person that is maintaining this particular application, then you want to err on the side of simplicity because you want to make it easier on yourself, and maybe you don't need as complex of a data model to run that application. You want to consider if you have shared or hosted resources. So how large is the data that you're working with? Is your application running at maybe 30 or 100 actions per hour? Maybe you don't need to apply some design patterns because you don't have that much traffic. And similarly, your expected scale. So when you take a look at your production logs, when you take a look at your predicted scenarios, if you do have larger numbers, then not larger numbers, then simplicity is where you would want to go. Can we zoom? No, that is there. Now, if you are modeling for performance, you obviously take a look at the opposite, right? If your project is larger or distributed, then performance is going to be of the utmost importance. If you have a larger team or distributed team, if you have more people to be able to help you develop this data model, more sources of input so you are sure that the workload that you're working with is accurate and you can get those predicted scenarios in order and quantify and qualify all of them. If you have sharded clusters, or if you're dealing with multiple regions, again, the larger your data size, the more likely you're going to need a data model that is designed for performance. And if you have an expected scale that is reaching, those multiple thousands per second requests or petabytes of data, then performance is something that you would probably want to model for. If you take anything away from here, it's err on the side of simplicity. Don't go right into the design patterns right away. Start out, maybe not even go through to phase 3. You can do phase 1, phase 2, and just continue to iterate. Once you start finding bottlenecks, once you start keeping track and seeing changes in your state, then you can go back and try to add some type of design pattern to your data model to add in performance. So when you do choose simplicity, what you want to do is you want to focus on the most frequent operation. So in your list of the operations that you've listed, that you've quantified and qualified, find the one that is the most frequent. You want to embed most things as part of your data model. And again, if it makes sense, only use one pattern if you really need it, maybe something like the document versioning pattern. And of course, for performance, you'll want to do the more detailed version of this methodology, right? So you want to consider all operations. You want to list out every single one. You want to qualify each one. You want to back that up and comb through your production logs and statistics. And you want to make note of everything. You want to embed and link as necessary. So remember, if you're reaching the 1 to zillions type of relationships, you're going to want to link most of that. Whereas all the other portions you may want to embed when it's 1-to-1 or 1-to-many relationships. And you want to use as many patterns as necessary and as needed. So you'll find as you're modeling for performance, you may be applying 5, 6, 7, maybe you apply all of the patterns depending on how your data is accessed and used, and depending on if you continue to iterate your data model because the performance is still dragging. Who wants both? Yeah, we all want everything, right? We want our cake and eat it too. So if you want to model for simplicity and performance, it's pretty self-explanatory. You're going to fall somewhere in the middle. You want to make your data model as simple as possible by following these things. You go through most operations and you quantify them. You embed and link as necessary, and you only use maybe a few patterns. And again, I can't stress this enough, you only start to apply more if you find that you are starting to find some performance issues, because that's where you'll start to see some changes as you change your data model. And that is it. Salamat. That means thank you in Tagalog. Thank you for bearing with me. I hope you learned something new. I'm happy to answer any questions.